All right, College Kim, we are back for another video. This video is going to be all about what we call Dalton's law of partial pressures and mole fractions. So I'm going to probably end up splitting up this video into two parts because it might be a little bit longer. So let's get started. Here we go. All right, on Dalton's law of partial pressures, on this handout, I want you to have this handout in front of you. Here's what I would like for you to do. I would like for you to pause the video and answer questions 1 through 5 on your own. So pause the video, try to answer questions 1 through 5 by looking at this model, and then come back to this and I'll run through the answers. All right, hopefully you paused and now you're back. So let me kind of run through the answers to this model 1 to just make sure that you kind of got the big picture items of this handout. It says when gas A and B are mixed, what's the total pressure inside the mixture? And if you're having trouble looking at this, here's basically what's going on. We have gas A on the left in this container and gas B on the right. And what's going to happen between the left and right side of the diagram is that this plunger up here on the top is going to go down. And as it does, it's going to force gas A into the same container of gas B. So on the right here, this is a mixture of both gas A and B. Okay, so if gas A and B are mixed and they're put in the same container, what's the total pressure inside the mixture? All you have to do is look at the data right here, and the total pressure is 1.5 atmospheres. And then it says what fraction of the total pressure is due to gas A? Well, if you look on the left here, you have 0.5 atmospheres of pressure that comes from A. And you look on the right side, that total pressure is 1.5. So here's what we're hoping you do is you take 0.5 divided by 1.5 and you go, hey, that's a 1-to-3 ratio, right? So a third of the pressure must be coming from A. I'm going to put it in decimal form, 0.33, same thing. In science, we tend to like decimals instead of actual fractions, right? And it says how many total moles are present within the mixture. So I look at my data on the right side over here, and it says I have a total of 0.90 moles in my mixture. And then the question is what fraction of the total moles is contributed by gas A? So if I go back to my left side here, it looks like I had 0.3 moles of gas A, and then the total amount was 0.9. Hey, look, that is also 1/3 or 0.33. How do answers 2 and 4 compare? They're the same, right? And why do you think that's so? Well, what's causing the pressure? It's all about the particles. And since a third of the particles in our mixture is gas A, then it would make sense that a third of the pressure is coming from the collisions with the container of those gas A particles. So if the portion of particles is a third, then that pressure portion would also be a third. And that is kind of where we get into kind of the beginning of our handout here. The mole fraction is a term that is probably new to you. Mole fraction has to do with the fraction of one particular gas out of the total number of moles in a container. So what we did with gas A, the mole fraction there was 0.3 out of 0.9, which is a third. We use a capital X. It's actually a Greek letter chi, but usually when we type it out, we just use X to represent mole fraction. And what mole fraction really is the amount of moles of one particular gas out of the total moles in the container. And that's going to be really important. So here's two equations that are going to show up in this handout that you really need to know. This first equation here, this is called Dalton's law of partial pressure. And the idea is that the total pressure in the container is just the sum of all the individual gases, pressures in the container. So if we happen to have 3 gases in there, if we were to take the pressure exerted by gas 1, the pressure exerted by gas 2, and by gas 3, add them all up, that would give us the total pressure. That is a pretty straightforward, pretty easy concept. The sum of all the pressures gives us the total pressure in the container. And then this right here is a part of it also. This partial pressure from the gas is really related to the mole fraction of the gas. That's this value here times the total pressure in the container. So if we want to get the partial pressure of a gas, here's what we have to do. We have to know the total pressure in the container, and we multiply it by the mole fraction. So if our total pressure back up in the top was 1.5, total pressure was 1.5 atmospheres, and we found the mole fraction to be, hey, it was a third, so 0.33. To get the pressure of gas A, all we would do is take 0.33 times 1.5. Hey, that would give me 0.50 atmospheres, and that would tell us what pressure just that one particular gas is exerting in the container. If the other gas was 2/3, 0.66, you would multiply it by 1.5 and you get 1.0, and that kind of makes sense accordingly. So I don't think you're going to have a whole lot of trouble with the sum of all pressures gives us the total pressure, or the pressure of an individual gas is the mole fraction times the total pressure. Let me go ahead and run through a quick sample problem with you. I'm going to run through question 7 on the handout. Here's what it says. A physiologist prepares an atmosphere, so a container of gas, consisting of the following gases: 79 moles of nitrogen gas, and then 17 moles of a particular isotope of oxygen. This happens to be oxygen 16, and then 4 moles of a different isotope of oxygen, oxygen 18. If the pressure of the mixture is 0.75 atmospheres, that's the total pressure, we're going to calculate the mole fraction and partial pressure of one particular gas in this mixture, this one right here, oxygen 18, okay? In order to get the mole fraction of, I'm going to just do oxygen O2 18, it's another way to write it. The mole fraction of oxygen 18 is going to be the moles of O2 18 over moles total. So what I have to do is just take how many moles of oxygen 18, hey, that's 4 moles, over my total moles. Well, when I add up these total moles, I get 100 moles. So I'm going to put it over 100 moles total. Well, then the math is pretty easy. I don't even need a calculator. I'm going to keep my 2 sig figs. 4 divided by 100 is 0.04. Keep my 2 sig figs. I get a mole fraction of 0.040. Question becomes, what is my unit? Well, if you look closely here, moles and moles cancel out. So actually, we don't have a unit, okay? So my mole fraction, you can think of it as it's 4% or 4.0%. And then if I wanted to get the pressure of oxygen 18, what I'm going to do is I'm going to take the mole fraction of O2 18 times the total pressure in the container. Since my mole fraction is 0.040, I'm going to multiply that by the total pressure, which we said was 0.75. And if I punch that into a calculator, basically what I'm doing is I'm taking 4% of 0.75. And I get 0.030, keep my 2 sig figs, atmospheres. That is the pressure of just oxygen 18 in that mixture. We could go through, if we really wanted to, we could do the 79 moles of nitrogen. That would be 79% of the total, right? And then 17 moles of the other one would be 17%. When we get finished, if we were to take the individual pressures, they should sum up to the total pressure of 0.75, okay? That is kind of big picture, mole fraction, how you find it, pretty easy. And then using that to find the partial pressure of a gas, Okay. Now, another big concept, let me go ahead. I think I'm just going to do one video here because I think I can do this all in one. We're going to look at this next model on your handout. This is kind of what's important in terms of putting this all together. If we wanted to collect a gas, that's kind of hard to do. We're doing a reaction and it produces a gas. So here's the process that we would go through. Let's say you had a reaction that was in a test tube and it was producing a gas, and we wanted to actually collect the gas. Here's what we would do. And if you kind of look at this picture, we've got a test tube here that's being heated up, and that is causing the reaction. And what's happening is that this gas that's being produced, we're putting it through kind of a little tube. And then if you look at this right here, this kind of looks like a test tube, or maybe potentially we would use a graduated cylinder upside down. And the idea is that if you fill that with water first and then bubble a gas into it, what happens is the gas goes to the top of that test tube or graduated cylinder, and then the water gets displaced by the gas. And at some point when the reaction stops, this little level here where the gas is, you want to figure out how much volume is in that container. Okay, so we'll actually do a lab probably where we use a graduated cylinder. There's another fancier thing called a udiometer, which is a really, really long test tube looking device with marks on it so you can read volume. And you fill it full of water and you turn it upside down, and then you displace with a gas. And what that does is, as it forces out water, you can read the volume of how much gas you collected. There's a really, really important step in here. And if you look at the part 2 here, is that you've got the pressure of the atmosphere pushing down on the surface of the liquid. And inside the test tube, you have the pressure of the gas also pushing down. We have to make sure, so you raise or lower the test tube to make the water level outside equal to the water that's still in the test tube inside. Why we do that? We want to make sure that the pressure inside and outside of the test tube or the graduated cylinder we're collecting the gas in is equal to each other. So this picture right here is what I'm trying to communicate. We want to make sure that the pressure total inside the container is equal to the pressure outside the container. Well, what's in the container? What's in this test tube? It's not just the gas. Because here's the problem. Water also turns to vapor. So the pressure total inside my container, as I've collected, is actually the pressure of the gas, but also water vapor. Water vapor is also in there, and there's nothing we can do about that. That's just how it is. When we collect a gas over water, which is what we're doing, we have to consider the fact that water vapor is also in the container with our gas. It's in this test tube or graduated cylinder right here. So how do we find the pressure of just the gas? Well, that total outside pressure, as long as the water level is inside and outside exactly the same, these water levels are the same, we can take a pressure reading from a barometer, and that is our total pressure. And then what we do is we look up the pressure of water vapor for a particular temperature. We're going to look it up on a chart, or it has to be given to you. That is something that we know at different temperatures, there's different water vapor pressures that we can use from a chart. And so for that, then if we know the total pressure and we know the water vapor pressure, we're just going to rearrange this equation. It's going to look like this. To get the pressure of just the gas, we have to factor out, we have to subtract out the water vapor that's also causing pressure in that container. So we take the total pressure from the barometer minus the water vapor pressure, and that gives us the pressure of the gas. Once we do that, then we can go ahead and do the rest of the problem with, since we know the pressure of the gas, we can use PV equals nRT, and we can do some of the math and the stoichiometry type problems we are going to be doing. Okay, so important concept here. When you collect the gas over water, we have to subtract the vapor pressure of water to get the pressure of just the gas. That's an application of Dalton's law of pressures, okay? All right, so I'm gonna kind of scroll down here and we're gonna do a sample problem together so you kind of see where we're headed with these type of problems, and then you should be able to do the rest of this on your own. So we have a reaction here of acetylene. Acetylene is C2H2. It's produced when we take calcium carbide. That's what CaC2 is. Calcium carbide actually reacts with water to produce the acetylene. It also produces some calcium hydroxide. So this is the reaction we're looking at. And here's what it says. For a sample of acetylene collected over water, what is the total, or the total pressure of the, with the barometer is 738 torrs. And then we are given the volume of this collected gas to be 523 milliliters. So we have a volume, we have a temperature, we have a total pressure. And here's another thing that's given. The vapor pressure of water is 21 torrs. So this is always going to have to either be given or a chart that you read based on the temperature of the water, okay? So it's just like the picture we saw up above. We're bubbling acetylene into an upside down test tube or graduated cylinder, and we take that reading of 523 milliliters. The first thing we're going to do is we're going to find the pressure of the dry gas. When we say the dry gas, that means just the gas without the vapor pressure of water in there. So go back to our Dalton's pressure law, Dalton's law of pressures. The total pressure is equal to the pressure of the gas plus the pressure of water vapor as we collect it. So there's really only two gases causing that total pressure. To get the pressure of the gas, what we're going to do is we're going to take the pressure total minus the pressure of our water vapor. Since we have these numbers, we can do this. 738 minus 21. We punch this into a calculator. 738 is the total pressure minus 21. That's the vapor pressure of water. We get a number of 717 millimeters of mercury. This is just the pressure of the acetylene in that container. And then it says use the pressure and the ideal gas law to determine the moles of acetylene collected. Here's the ideal gas law, PV equals nRT. We know the pressure because we just calculated it, 717 millimeters of mercury. We know the volume, it's given as 523 milliliters. We know the temperature is 23 degrees Celsius, and we're trying to solve for N. We also know the R value. Remember, the R value is a constant, 0.0821 liters times atmospheres, moles times Kelvin. Those are the units that we're going to have if we're going to use this R value. So here's what I'm going to do. Out to the side over here for this pressure, 717 millimeters of mercury, we need to get rid of, so we're going to divide by 760 and multiply by 1 to get our atmospheres. So 717 divided by 760 gives us a pressure of 0.943 atmospheres. We're going to have to use that in our calculation. The other thing we have to deal with is temperature is 23 degrees Celsius. We're going to have to add 273 to this, which is 296 Kelvin when we plug that in. And then the volume should be pretty easy. We've got to get it in liters. We're going to move the decimal over 3 places, and we're going to get 0.523 liters. All right, so I'm going to rearrange my PV equals nRT equation. I want to get N by itself. So I'm going to divide both sides by RT, and that allows me to set it equal to N. So I'm going to plug in my numbers. My pressure we just found was 0.943 atmospheres. My volume is 0.523 liters. My R value 0.0821. And then my temperature 296. We plug all this into a calculator, 0.943 times 0.523 divided by 0.0821 divided by, since it's on the bottom, 296, you get 0.0203 moles of this C2H3. That's how many moles would have been collected. The next question says convert these moles to grams. So 0.0203 moles. We need a molar mass of acetylene, okay? All we need to do is 2 times 12.01 plus 2 times 1.008 on a calculator. So 12.01 times 2 plus 2.016 gives me 26.04 grams per mole. I'm going to multiply that by 0.0203 and I get 0.529 grams of this acetylene. So that's how many grams I'm going to have, 0.529 grams of acetylene. And then we have one more question here. It says use the mole ratio to determine the mass of solid calcium carbide that was necessary to make this much gas. So here's what we're doing. We're going to go back to, we know we have 0.0203 moles of C2H2 produced. If you go back up to this equation, we're going to find the mole ratio between C2H2 and calcium carbide. And if you look back up there, it's actually a 1-to-1 ratio. So we still have that many moles of calcium carbide. We're going to go one more step. Get rid of moles of calcium carbide and go to grams of calcium carbide. Out to the side, I'm going to look up calcium is 40.08 grams. And then we have 2 carbons. So to get my molar mass here, I'm going to take 40.08 plus 12 times, or 12.01 times 2, so that's 24.02. And that gives me 64.10 grams per mole. And I'm going to multiply that by my 0.0203, and that tells me I would have 1.30 grams of calcium carbide would be needed to produce that much acetylene, okay? So what's new here? The law of partial pressures, and to be able to find that partial pressure of a gas using mole fractions. And then specifically collecting a gas over water, we have to understand that we're not just collecting the gas, we're collecting water vapor. That's part of that pressure that exerts on the container. And so we have to factor it out, subtract out that water vapor pressure to get the pressure of the gas. And then we just do PV equals nRT. And in this case, we're doing a little bit of stoichiometry. All right. Thanks for watching.